In our last lesson on polynomials, we are going to learn how to graph them. So this first row of graphs is also in your book on page 453, and it gives you a general shape of what the graph of each type of function might look like. So linear, degree 1, obviously a line. We studied quadratics, degree 2, parabola. Cubic function, degree 3, I've also heard it described as a snake. And then we've got the quartic function, which can look like a W. It can also look like a parabola. If you've got the parent function, f of x equals x to the fourth, it's just a skinnier version of the parabola. So we're going to learn how to tell if it looks like a W or a parabola, and these points along the graph here, it's called a turning point, and that information is given with looking for values between the zeros. So when you look at where the graph crosses the x-axis, and I'm going to use these zeros because they're a little further apart. So we've got here and here. So you know that the function has to turn somewhere between those two x-intercepts in order for it to cross the x-axis again. All right, end behavior is determined by the degree, and that would be the functions that we have in our graphs, and the leading coefficient. So thinking about when we studied quadratics, if the leading coefficient was positive, it opened up, like in our picture, but if it was negative, it opened down. So the end behavior, thinking about what the graph does as x gets very big or very small, will change if the lead coefficient is negative. So it reflects it across the x-axis. Looking at the cubic function, instead of starting down and heading up, it would start up and head down if the lead coefficient is negative. So maybe I'll sketch a graph of each of the negative options. So for the parabola, it would open down. For the quartic function, again, it would open down. It could be a W, or it might just be a parabola. And then same for the quintic function. It would start up, maybe it would have a couple of curves, and end up pointing down. So that's what a negative lead coefficient would do to each of those graphs. It would make the end behavior opposite. Turning point I mentioned, where the graph changes from increasing to decreasing or vice versa. So here's my little note here for you. A polynomial degree n, so let's just say it's a quintic function. So a polynomial degree 5 has at most n minus 1 or 4 turning points. So a quartic function degree 4 would have at most 3 turning points. And our process for graphing. First, we'll determine the degree, which will give us the shape and the end behavior of the graph, and that just comes from the highest power in the polynomial. We'll solve for the y and the x-intercepts. Remember, substituting 0 for x to get our y-intercept, substitute 0 for y to get our x-intercept, and the multiplicity of the roots. What the multiplicity tells us is that the x-intercept is a turning point if the multiplicity is even. If the multiplicity is odd, it will just cross through the axis. And then finally, we'll make a table of values around the zeros to try and find any of those turning points, as I mentioned before when we were looking at the graphs. In the next video, we will take a look at all of this information and how to graph one of our polynomial functions.